so now we'll open up our file. So I'm going to, I clicked on the add file icon, it just brought up our window here, so we're going to search through and we're going to access file. We're going to switch our extension to .jet, and then we're going to choose this file. So when we bring it up, we have the file name here. We can bring up multiple files. If we bring up multiple files, they will all be shown in this, and we can simply access them by clicking on the file name. And so we see here, this is the raw data. So we have time in seconds in our left column, and in the right column we have the raw heat rate. So now we're going to switch to the Analysis tab, and you can see here is our raw graphical titration data. And each peak corresponds to an injection event, and the upward facing peaks are exothermic. And you can see that we have he's telling us we have 25 injections, and each box here around each peak signifies our injection interval. So first, just looking at this data, we can say, okay, well, we see a titration curve, it looks good, we'll be able to model this. Data quality, it's okay, but this is definitely something we can use to model. So first, let's just take a look. We'll subtract our baseline just to see what our baseline looks like. So without the baseline, you can subtract the baseline. It's a fairly flat baseline. Let's click it off for a second. And so now, if you look at the data, we have large peaks, and then we have our data going back to a baseline. And we're actually integrating these baseline regions too. If we zoom in, you can see that we have regions where we're integrating all this region here. Since we have such big heats, it's probably not going to make a difference, but we would like to more accurately model just the peak area. So we can zoom out, click here for zoom out, and we're going to adjust our interval regions and set a new baseline. So we're going to click our new baseline icon, and we have our new baseline window pops up here. So it's asking us to fill in these parameters. So we have our first injection region, starts at 300.
Integration region.
And then our integration region width, it says this is what we want to change it to. So we would be integrating, currently we are integrating all 300 seconds. So first let's just change this to 200. And then the integration region interval, that's what we set during our ITC run when we set up the actual experiment parameters. And we can leave this region blank if you want to just for all the regions. So we're going to hit OK. And when I do that, you're going to see that two things are wrong here. First, you can just look at the data, and we obviously set the wrong time to begin the integration. And also that, so I'm going to go and I'm going to fix that. First, I'm just going to get a better idea of when the first integration region started. So after about so it was actually more like 250 seconds. So we're going to go back in here, and all I do is just fix this, and then I'll click OK. And then when I zoom out, so you can see here, this looks much better. All the peaks, so still some of the peaks are in the range. It's obviously peak region was not precise. As you can see here, so we have, let's just zoom in and we can take a look. So generally the peaks seem to be, see, they're out of the integration region. So there must have been, during the data collection, maybe one of these intervals is slightly off. So we'll just go ahead and we'll set that. show you what happens when you put a few of these in. So we can just go ahead, we'll select a bunch. This data set obviously is not as good as I'd hoped. So we'll use this one. So, but you can see here we can have multiple data sets, and now we're going to go ahead and we're going to fit a new integration region. So we still have, these are the same, but before I do that, let me just double check and make sure everything is set. So that's 300 is when our first injection is. We have 100, 200, 300, and then each integration region is 300. So now, it's much better. So you can see that we're shorting the integration region, so we're integrating less of this baseline. We can actually go a little bit smaller too, and integrate more precisely the peak area. So let's see what happens if we go down to 150. So we're just integrating the peak region. You want to make sure that you zoom in, and just make sure you're not cutting off any of the peaks. So we can zoom in and look really close, and then using this bar on the bottom we can just scroll across the data and just take a peek and make sure that the baselines are approximating the noise here. With data that we have here, we don't have to really worry about trying to fit a baseline so precisely, because we're getting our heats are so big that relatively the baseline is fairly flat. So you can see here. So now we can click over to the area. So now we have data that we can now begin to analyze. So we can click over to our area window and just make sure everything looks okay here. So just, we have 20, seeing here we have 26 injections, we have 25, so let's go back and look and see why that's the case. So we'll unclick our baseline. So it's including, we had a 300-second final baseline we put in, and it's counting that as an integration region. So we're going to get rid of this 26th region here. So we go ahead and we're just going to delete an integration region. Go over and we click, and now it's gone. So let's go back to the area. Okay, we have 25 injections, 10 injections. Alright, and these are just the moles of the syringe in the cell, and this is the molar ratio and our cell volume. So everything here looks okay. We have our exotherms are pointing up. If you want your exotherms to go down, you can simply click that and the exotherms are going up. Okay, so now we can go over and model, begin to fit our data. So we can take a look at our data here. These are the integrated peak regions. And you can see here we have this small deficient peak here. This is common in ITC, and this is due to diffusion of the titrant during equilibration. So we're getting because of the diffusion, we're getting smaller than an expected injection. So we can gray that out. So we're just graying that out. And now we're going to fit this data so that we can determine a K, a delta H, and the N of the interaction. So to access a model, we're going to go over the model window here, and we simply click the mouse on the star, and this brings up the model manager. So we expand the model manager window, and we have several models, and we're going to choose the independent model. The independent model is just an independent site binding model, and we're going to select, it's a one-site binding model. It assumes that all the interactions are happening similarly with the same enthalpy and the same K in stoichiometry. Okay, so we have our model here, so we're going to fit that. But before I do that, I'm going to just move this box out of the way. And there's several icons over here, and each does a different little thing, changing, making type smaller, making type larger. We can move the legend around, so we can move it over on the side, on the top. And this is going to move the key here, so we can click it, put it where we'd like. I'm just going to leave it here. So now we can go ahead and fit this. And to fit this, all I do is go to this fit icon, and I'm going to just click that, and now we're beginning to fit our data. So you can see that the model begins to just find the integrated points. And so now it's caught in a local minimum now. So we can simply just say stop at local minimum. And that's basically, it's going to stop at the best fit at that point. The local minimum, we're caught in the local minimum, you saw how it was jumping there. And that's just basically the local minimum in the calculations that wasn't allowing the program to proceed. So based on these preliminary data analysis, we have our K is about 6.1 times 10 to the 5. We have a delta H around 10 and a stoichiometry of about 1. But looking at the data, you can see that there's, clearly we're not modeling these points very accurately, and this is going to overestimate the magnitude of the beginning injections and to the saturation, and this is ultimately what's going to determine our delta H. So what we want to do is to better model these points, we're going to input a second model that will average the points together, and that will be combined with the independent site models. So here we have selecting this blank constant model, and this is essentially a straight line without a slope, so it's just going to be a perfectly straight line. So now I'm going to fit again. You can see we have our second model here, and when I fit this model, what you're going to notice is that the points over in this region we'll be able to model those a bit better. So I fit, and now you see we have 3 plots here. We have I'm going to unclick local minimum. So now we have 3 plots. We have the blue one, which is our independent sites model. We have our red one, which is the blank constant model. And then we have this dotted line. So when it starts stuttering like this, you can click stop at local minimum. It's going to go to the best fit at that point. And then we have the dotted line, which is the sum of the 2 models. The lower plot here, this is the basically the deviation around the fit of the models. Deviation's the points around the fit of the models. And this is going to calculate our standard deviation of the fit. So with these calculations, we have a K. There's a bit more accurate fit here. So we have a K, it's a little bit different than before, 1.7 times 10 to the 5. Our delta H about negative 8.7, and our stoichiometry is about 1.03. And our blank constant, that's just the, basically this is our heats of dilution, of like negative 11. So this is how you would model a typical data set, and this is the same, although this is an acid-base titration, this is the same procedure you would have of a one-site binding model of a ligand and a protein.
Is this fairly typical to combine models? Because I don't remember us doing that with the Origin software.
I'm not sure about what their fitting algorithms were, but I think that this was because what you're doing with this one is sort of it's putting in the value for it's almost like you're calculating the heats of dilution on some level. Because you see, before we had our fit was just completely off. It was off. We were missing this bit totally, and that might have been, maybe the shape of this curve is always just going to fit roughly sigmoid shape, and we're just maybe forcing it a little bit for a better fit.
But, yeah, I'm not sure because each equation is set up so that the parameters mean, the variables are the parameters, and as you fit. But if you have 2 completely different equations and you're somehow merging them, I guess I don't understand enough about that, how there isn't any conflicts between how those equations are merged and how the
actually, when you
defined.
do with this way, you actually are getting, when you do, if you don't merge these 2 models, you're not close to the published values. You're off by a bit. The enthalpy will be off, and the K is going to be off.
Does this report a chi-squared error anywhere?
We don't use a chi-squared. We use a standard deviation. So basically, the fit around the line. The newer software has a statistics button here. And that'll give you confidence intervals for each of the plots.
When does that software come out?
That's on the software.
Okay. Can you load that before you leave?
Yes.